Okay. So today we're going to talk about the derivative, and we started this journey on the derivative already last time. So the important part here is to understand that there are two ways to look at the derivative. One, the way that is in the book, and we'll discuss it today a little bit, whereby we derive the derivative, the concept of the derivative as a graphical intuition, and then from that graphical intuition we derive a algebraic characterization, or the formulaic characterization of what the derivative is. So usually when we teach and learn mathematics, we can do it in one of several ways, but the two more common ways are which very roughly speaking, roughly divided, are the algebraic intuition and the geometric intuition. Algebraic intuition meaning that we have these symbols that symbolize the abstract concepts, and then we use formal language, or the formalistic approach to mathematics, by manipulating and seeing that, okay, we can rearrange these symbols in a certain way, and then we get the proof, so to speak, that something is equal to something else, or something is smaller than something else, or something like this, or some set contains other things. And we do this by use of certain rules that we have learned are holding inside the language of mathematics, if you will. A lot of it is grounded on formal logic sometimes, but really, I mean, most mathematicians do it in such a way that they're not making a big deal about the formalistic approach, and the proof is just, every step of the way is every step in a proof or deriving some concept is done kind of mixing intuition and strict rules about how formulas can be manipulated. But having said that, we're going to use the classical way, but I'm focusing less, perhaps, or not less, but the book is very heavy on the geometric intuition, where you draw a picture that resembles a situation, and you draw on you kind of try to gain the idea of what's going on by looking at the picture and understanding the symbols' relation to the picture. And whereas this is actually a pretty good idea and a pretty good way of learning mathematics, it gives you something to think about and gives you this feeling of understanding. I do, however, personally feel that this leaves the student with a false sense of understanding, unless it is fully backed with the abstract thought, at least towards the end. So the abstract thought that I want to convey here, at the very core of it, is the concept of linearity. And just to make it very simple here, in this case, I defined a linear function, or linear mapping. If it has this property that you have addition and multiplication inside here, addition and multiplication are applied at the domain. And then what it comes down to is you can multiply and add at the codomain. So linearity means that addition and multiplication from the domain are lifted to the codomain. And now this could easily be, I'm not sure how familiar you are with vectors and manipulating vectors, but here the domain could even be real valued vectors. They may be, three-dimensional vectors. We can add those, and then we can multiply. In that case, this A and B would still be real numbers, but X and Y would be vectors, right? So in that case, we would be multiplying the vector X with real number A, multiplying the vector Y with real number B, and then taking the linear mapping from that. And it maps somewhere, and this could be another different dimensional space with vectors, or it could be the real numbers or whatever. This linear mapping, I don't know what this L is. It's a function that maps these elements to these. And in this, my definition, it's real numbers, and it could be vectors as well. But it's called linear if addition and multiplication here can be applied, you know, after the mapping. So that, okay, there's an element of that space, you're multiplying with a real number. There's another element of that space, you're multiplying it with that real number, you're adding them together. So you might as well take the mapping from this X directly and this Y directly, and then multiply whatever you get with A and multiply whatever you get with B and add them together. This is the core of what linearity means. It's really important. But then when we talk about real numbers, then in fact, all linear functions are simply multiply X by some constant. And you can check that it's definitely linear in that case. So this way, you know, graphs of linear functions are always straight lines. So this ties the concept of linearity to the idea that we are looking for a certain straight line. So let's move to this book, and oh, I had it in the wrong page. It doesn't matter. I'll just go upwards, or do I go down? I go downwards. Sorry. I thought I had left it at the correct page. Terribly sorry about that. I was supposed to do the damn. Sorry. I have to go down to the. So here. So we're kind of moving in this idea that if you see the picture now. So we're moving in this idea that we're drawing a straight line between 2 points on the graph of the function. So basically there's a value A, which the function maps to Fa. There's value X, which the function maps to Fx. So if we move from this point to that point via a straight line, then on the way from A, Fa to X, Fx, if we're moving on the straight line, we're not going to be following this curve directly, right? We'll be incurring a certain level of error here in between. So this is called the second line or secant line. It means that it connects 2 points on the graph here. And really, you know, this line in between here, that's the secant line. So in between there, it's an inaccurate representation of this function. So if we approximate it with this, in between there, it's an inaccurate representation, right? So it doesn't follow quite the line. But the idea here is that if we zoom in closer to this, the closer we zoom and the shorter we make this secant line, then if the function is differentiable, then the error here in between, here, in this region, because that region becomes smaller, then the error that happens between A, Fa and X, Fx, that error becomes smaller and smaller. Well, that's obvious. I mean, if it's continuous and behaves in a reasonable manner, this function, then that's obviously something that might happen. But it's not that obvious. Some functions do not have this property. Okay? And we're going to see what we can do about that. I'm not going to talk about the secant line anymore. More here, I'm going to just move along to the actual concept of derivatives and so forth. I'm not going to talk about we're going to move to integrals shortly. So skip the limit idea because we talked about the limit. We know how to calculate limits. So we're really going to be looking at, sorry that I did it like this. This book is not in the order in which this book covers this topic. It's not quite as how should I say? It's not quite as quite the order in which I prefer. Okay. I'll still. So we're going to be looking for what is called the tangent line here. So as long as we are moving from X to A, then there's a distance to be covered, right? So this Q here is the basically called the difference quotient, and it's the slope of that secant line, right? So you move x minus a, you might move that much to the right from x to a, and the function grows from fx to fa. That's what happens. So if we mark it so that we're moving the step from x to a, the distance is h, or from a to x, if you will, is h. Then we can express this, if we choose that, in this case, x equals a plus h, then we have this difference quotient can be given like this, and the h is the increment. It's the distance that the second line, the secant line covers, right? This is what we're going to be looking at. What happens to this when h goes towards 0? And it's worthy to read all of this, but we really are interested in what happens. So if we draw the secant line like this, it's a relatively long slope here, long line, and there's a lot of error there. But if we start moving this point here towards that, and we draw the secant line here, so you see that the line, the error between here is starting to get smaller and smaller until such a point we actually reach this. And if we think that the slope must be continuous and it only hits this at one point, one single point locally, of course it can hit somewhere, maybe this curves down and we hit it again, but here locally we are only hitting it at one point. So that slope is what we're looking for. We're looking for basically the direction. Where does this locally point to, this line, this graph? And it's this what we call the tangent line. So here's an idea, and this is relatively good place to stop. So if you look at this, we're looking for the square root of x, and we're looking at the slope at around the point x equal 1, right? So you see what is happening here. The error here starts to grow. If we look at this, it's touching on that point over there. And now this is the tangent line, so it's touching in one point only. So if we move from that point to the left or to the right, there will be error if we think that, okay, let's say the function is roughly this, but it's starting to bend down. In this case, it's bending down away from that line if we go left or we go right. So what happens if we start zooming in on this point? So the point 1 is somewhere in here. We zoom it, and once we zoom it a little bit more, we see here that the error has become smaller on both sides. And even though we zoomed this, so this is a rather large zoom. So here we had 2 units on this, but now we only have 1.2 units here. So if we zoom again, so here we have 0.1 units here, and it's already starting to resemble a straight line. So what's going on here? So let's go look at the definition that I gave earlier for the derivative. So I said that if we have a continuous function here at some interval, and let's look at this definition. So I'm saying here, in essence, it's continuous. Let's say it's continuous inside this box. That's the interval here. And let's say h is the width, if you will, of this box, because that's how much. Here we jump for 2, but in here we jump for just 1, and in here we only jump for 0.2 and so forth. So we're kind of making it smaller and smaller, this jump, left and right jump. That's the h. The h is the scale of this picture. And if you look at this definition, so we're looking at the values at the edges of that zoomed in area, x plus h. So h can be negative or positive. It's in some direction. And fx, well, at the center of the image, at x, that's your f of x there. And then as you start moving away from it, along the straight line, this is the linear mapping there, you incur some error. I mean, f plus at x plus h you know, it's something. So if you move along the straight line, this is where you get. But then this is how much the straight line deviates at the edge of that region. So that's the h is the zooming in factor, and rxh is the error in this this picture. So let's look at the here. We clearly see that despite the fact that we are zooming in closer and closer, so the h becomes very small, the error that is visible is still extremely small. It's becoming smaller and smaller. So that means, see, the error itself might go to 0, but it's not enough. It must be that the error times the scaling factor must go to 0. So this is the intuition that I tried to explain last time, that it's differentiable. The differentiability means that if you approximate it with the straight line at that point x, and you zoom in closer, and despite looking at it closer, and you try to look at there's this tiny error, and you look at it closer. When you look at it closer, then the error becomes still smaller and smaller, even though you zoom in. So you're kind of looking at, in this picture, you're looking at it from a very, very close distance, but still there's almost no discernible error here. So the function flattens out, right? So the tangent line here, that's the limit here. That's the slope of the tangent line. And I defined this Lx here as the derivative of f. So that's the slope of the tangent line. That's the derivative. And if we derive this following this definition, so we solve, we know, knowing that this is supposed to be linear, so this has a slope. We're looking for this L of x, so it's some k of x times h, right? So, because this k of x is something, I don't know, it depends on x, but this function is some constant times h. And we're looking at what that constant is. So we rearrange this terms from this algebraic intuition. So we rearrange these terms and solve for this L of x of h. So simply move everything on the other hand side. So it becomes f of x plus h minus f of x minus then this scaled error, right? So we know that this here is some kx times h. So we know that this kx is this, but the error factor is here, so we need to get rid of that. And the way to get rid of that is we look at what happens when the kx doesn't depend on h, so it shouldn't depend on h, right? So it should be the same regardless of what h is. So we let h approach 0. And here, this, if we divide this absolute value of h times rxh, we divide it by h, then, you know, as long as h is positive or negative, then this can be eliminated, and it's just either positive or negative of r of x. But we know that this rx of h goes towards 0 anyway, so we can just drop that because that's in our definition. And what remains is this limit as h goes to 0. So this is the algebraic intuition, if you will, and here was the geometric intuition, if you will, of the derivative. So we're looking at the slope of that. So let's go down and let's follow this now. Here are some examples. So we find the tangent line. So here's an example. Find the equation of the line tangent to the graph f of x equals x squared plus at x equals 3. So we can go directly to the slope of that. So again, I refer you to this. So we can forget about this error here because we're just looking at the tangent line. So this is how we follow the tangent line, right? So we find the tangent line there. So at x equal 3. So we let x approach 3, and x is now, that's our, basically, x is now the 3 plus h, right? So we have f of x minus f at 3, and then the further this x minus 3 is now the h, right? So we let, as x grows to 0, then x goes to 3, then x minus 3 goes to 0, right? And we can substitute this x squared and 3 there. We get this limit, and then we can subtract that x minus 3 from there. We get x plus 3, so the limit is 6. So the slope is 6, right? But where does the line, what's the line? Well, the line, that's the slope of the line, but we need to find what that actual line is. Well, it has to go through that 0.39, and it must have the slope 6x. So we can solve this. This is fairly easy. Y minus 9 must be equal to 6 times x minus 3, obviously. So we say we can simplify this as y is equal to 6x minus 9. That's how we follow it. So that's the equation of the line. The equation of the line I find a little bit uninteresting. You can draw this if you like, and that's another thing. But from the point of view of the derivative, I do not believe that the concept of the line, tangent line, how you find the exact line and where does it go. I mean, it's just a line. We know its slope and we know it goes through that point. You can solve that, I hope, from your previous experience. The important part is finding the slope. And you do that by the derivative. So let's go on. There are other equations and examples here. There's a 1 over x. I'm not going to go there. So we can just think about the concept of this L of x, right? So the slope, the kx, which I mentioned there, and the slope there, that is what we call the derivative, and it's a function of x. So in some sense, we can think of the derivative as a function. We can say that the process of finding this limit in this case is called differentiation. So we find the derivative of the function. Well, this can be done. While this can be done at a particular point, I see no point in us going through a lot of examples where you do it for particular points. There are plenty of examples, and I really do urge, if you find this intuition a little bit hard, to go through all these examples and see how it's done. But I would rather skip that part, and I would rather discuss first some of the applications of the derivative. We'll have one group session shortly, but first, well, okay. I think we'll have a group session now, because we can then talk about these velocities and rate of changes there. Let me just see if I have give you some exercise to do here in groups now. So in these cases, find the slope of a given function at a given point. And now I'm not going to ask you to find the equation for the tangent line. I just want you guys to find the slope of that tangent line, not just the slope, f prime at a, and do it with using the limit instead of many of you know how to find the derivative, so don't do it with the derivative, do it with the limit. So let's take this 23. So you have f of x is equal to x squared plus 9x. So I'll write it here. F of x is equal to x squared plus 9x. Use the limit to find f prime at 2. Okay, this is your group assignment. So I'm going to now divide you guys into groups. Let's resume. So you we're given the task of finding the f derivative at 2 for x squared plus 9x. And did you get my message about, I thought I'd give personally give a task for one person in the room to report what was the result of the discussion. So if you got that, then the result can of course be that no, we didn't get it, or you know, we didn't do it. So, but a quick explanation of how you did it, what happened in that, right? So room 1. Are you hearing me?
Yes.
So did you manage to do this?
Well, there wasn't many discussion in our group.
Oh, no discussion. Oh, that's
but we kind of understood how we should do it by taking the fx minus f
yeah.
to
Write what I mean, if you didn't find it, then just write what you need to find. What is the limit that needs to be found? Can you write it in the chat box?
yeah.
Okay. The same for the person in room 2. If you got the message and if you were able to discuss the idea of how to find it, what was your answer? What is the limit that needs to be found? And the same for room 3. Just write your answer in the chat box and we can discuss them. I'll explain or discuss them there. Okay, let's move along. Yeah. Which in, yeah, that's how you do it. Yeah. Which in this case, if you replace, well, the limit, yeah. So we can write it like this: limit of x to 2. Yeah. So, but in place of f, so that fx, so that x to 2, and it should have x squared, right? Plus 9x minus 2 squared plus 9 times 2 divided by x minus 2, right? So that is, yeah, alternatively that, but this is the limit characterization. So let's discuss how it's done. So we have this f of x there, and I'll just use pen and paper here. Well, I tell you what, we'll postpone this example a little bit. We go to the more generic version, and I'll tell this, we'll go through one of the examples. So see here, let's go up, 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 up. Let's go through this. So yes, the slope of the tangent. So it's really this m tan, and here you see, just like that, fx at minus f minus at f at 2. So this is basically the template of how you do it. In this case, it's here x is that, and we have this 2 to the 2 plus 9 times 2. That's f at 2. So this is in fact limit at x to 2 of, and now I'll just write it again, x squared plus 9x minus, and let's see what happens here. We have 2 to the 2, or it should have parentheses there. So we have the value of the function at 2 is 4 plus 18, right? So that's 22 divided by x minus 2. So there should be parentheses there. So we need to find the limit here, right? And it's far from being easy task to do, so we can leave it at that now. This is a nice exercise for next week. So you can, then you know how this limit goes. But it's actually far easier to just, I mean, this should show you that calculating it this way, the slope, is far harder than finding the derivative and then just calculating it. So that's why this is one of the reasons, and I want to stress this, that one of the reasons that in mathematics, why we derive these rules on how to do things by chopping them into pieces. Like earlier, we had the limit of the sums as the sum of the limits, and the product rule for limits, so that the limit of the product is the product of the limits, and so forth. So the same here is for finding the derivatives. It is far easier to find a generic formula for the derivative, and instead of always having to go through finding this limit. So it's good. It's a good idea for us to practice these limits, and I'll put some of these in the, sorry, I'll put some of these in the exercises for next week. But they are far from being the important matter of this, and or the takeaway message from this. This is what you can think of them as, this is what they mean, but because of the mathematics provides us with the powerful tools of abstraction, then we can actually learn how to break these down into their composites, find the derivative of those composites, and then, you know, just calculate it. So let's move along to that idea. So I really urge you guys to study these examples. These are this can really give you a good idea of the intuition of how it goes. Also, I want to mention here that this velocity characterization, so you can think of velocity as the derivative of the place that you are at a given time. So that's really what it is. Velocity is the rate of change of your position. And this is something new here. Here was also some estimation procedures. I would rather not do those here. We'll return to this when we talk about the differential equations later a little bit. So here was the rate of change of temperature was one. Again, not going to go into this. There was a given rate of temperature change. We had one example in the first exercise about temperature, which had the exponential function, and we'll see later that that comes from a certain situation that involves differential equations. But these are all valuable ways of making use of this. But I do not believe that the good idea is to use the limit to calculate these kind of very hard tasks, because this is just so error prone. It's much easier to then abstract away and then calculate the derivatives and use compositionality. Compositionality meaning we break it down to the smaller bits, do the hard stuff on those smaller bits where it's easy, and then combine it back to a larger formula, which is far easier than taking the larger formula and applying the limits to that larger formula. So I'm going to go down here on this material and towards this idea. We already discussed this derivative as a function a little bit, so let's just very quickly go through this. So in my characterization, I had this LXH. So that, have to understand, that's a little bit different from the derivative. If you want to find the derivative as a function here, then really here the slope kx, that kx is really that's really the derivative. That's really the f prime of x, is really that kx here. And to find out this, because this comes out at this depending on x. So it comes down to this. It's exactly the same as this derivative function. So given a function, when we take the derivative of that function, we get another function. which then can be used. You can explain that the meaning of that function is the slope of the original, so f prime, that's the derivative. So the meaning of this is the slope of the tangent line that goes through point x, fx. But you can also use this characterization that it's here, it's the, well, in this case, it's the slope of that tangent line, which we did when we assumed that this is real numbers. But really the derivative as a function is really this, it should be thought of as the linear operator. So when you're later going to deal with vector calculus and vector differential functions, so are any of you familiar with the term gradient from vector calculus? Okay, no one. Okay, well, you'll encounter it later. So you will encounter it's the idea there is it fits exactly this definition, but you can't really explain it in terms of this limit here. So the generalization, I want you to be ready for the idea of the generalization here. So, but we can use this limit to find the derivative function. And we say that this function f of x is differentiable at point A if the f prime A, that's the direct limit here, like in our example here, which exists. If it exists, then that's fine. But the idea is that we need to look at this f prime not just at point A, but in general as a, you know, what happens to this f prime at different points when x is certain point. So we can use this limit simply by leaving f of x here, x as an unknown variable and h is the only thing, and let h go towards 0. So when we have this, we can just calculate this, and if we have a formula for f prime of x, we can just substitute x for the value here. Like in our example, instead of calculating the limit as x goes to 2 of fx minus f2 divided by x minus 2, it'll be far easier for us. It'll be far easier for us to find f prime at any particular x and then just substitute x for 2, right? So let's find the derivative of the square root function. And these are all fun. These are great fun. So we're going to have great fun. I'm half joking. Some of you will be horrified. This is going to be great fun doing this. So we'll find the derivative of the square root of x. So we punch in here. So we find f prime of x is the limit as h goes to 0, and then f at x plus h, that would be the square root of x plus h, minus the square root of x. So we multiply both the numerator and the denominator with the square root of x plus h plus the square root of x. So that we can, if we multiply those, we notice that the numerator becomes x plus h, x plus h minus x, which then just results in h. And the denominator becomes h times the square root of x plus h plus the square root of x. And now we notice that we can cancel the h because it appears both in the numerator and denominator. So we are left with 1 over the square root of x plus h plus the square root of x. But as h goes to 0, this just goes towards the square root of x. And we get that this is 1 over 2 times the square root of x. So this is great fun. So, okay, but here's another example, finding a derivative of a quadratic function. I wouldn't go so far as to do this. You can look at these examples, but why would we go here? It's much more fun, much more fun to prove that you can actually apply the derivative in a compositional manner. I'm gonna go to this graphing the derivatives thing and this, because that's ridiculous. It's perfectly, we know how you would do that, but we are probably better off when we have certain rules to do that. But before we go there, let's go through this derivative and continuity. What is the connection here? So I mentioned here the definition. Let f be a function that is continuous on some interval and la da da da. Well, I assumed already that it is continuous on some interval that contains this point at which we say that it's differentiable. So really, by definition, if a function is differentiable, it has to be continuous. And it doesn't, it's nothing to do with this, how we define this other stuff here. It's simply because we say it must be continuous. And that's all there is to it. I mean, we don't really have any reason to try and justify why a differentiable function is continuous. We just defined it. Is for it to be differentiable, the definition includes that it must be continuous. Well, one of the reasons is that we want this limit to exist, right? And the limit at h approaches 0 must exist at that point x. So it means that the limit as x plus h, right, approaches x must exist. And, you know, it must be the same as the value of the function. Otherwise, it makes no sense, right? It doesn't make any sense if f at x plus h has a different limit than f at x, because we're dividing it by h. If it's different, if this doesn't go to 0, when h goes to 0, then this will go to some infinity, and it doesn't have a derivative. So it cannot have, unless f is continuous. So that's why we require it to be continuous. So if f of x is differentiable at the point A, then f is continuous at A, and that must be true. And because they didn't characterize here the assumption is that such that f must be continuous, then they can prove it, because they said that, okay, this limit exists. This limit exists, therefore, you know, f must have the limit as f of x must, as x approaches A, must be f of A, meaning that it's continuous. So, but there are situations where it's not so, that a continuous function is differentiable. In fact, there are functions that several continuous functions that are not differentiable. We can define functions that are so pathological that they're continuous, yes, on some interval at every point, but they're not differentiable at any point, which seems like it's impossible, but it's not terribly how should I say, they are not easy to understand if I say it like this, but when we construct it, it becomes obvious. And I'll show you later some examples. But let's look at the example where the derivative doesn't exist, and we already can see why not. And this conforms nicely to the characterization that I tried to explain with the idea that the slope, you know, the zooming in must result in the function looking like it's flat. So here's an example. F of x equals the absolute value of x. So it goes down and then it goes up. There's a graph of it. And if we try it with the limit characterization, so the limit as x approaches 0, and we have f of x, which is the absolute value of x minus 0. And we have x minus 0 here. So in fact, what we get is the limit as of the absolute value of x divided by x approaching zero, x approaching zero? Well, we already showed in the exercises today and yesterday, and in the exercises, the question is to demonstrate that this function doesn't have a limit at zero, because on one side it approaches -1, and on one side it approaches 1, and you know, there's no limit at zero. Pertaining to the graphical intuition, if we look at this picture here, that's f of x equals the absolute value of x, then no matter how closely we look at this function, we can zoom in here, and you know, we can zoom in however far we like, it will actually look exactly like this at all levels of zooming. So it doesn't start to flatten out when we look at the origin of here. We zoom in both x and y axis, that's h, becomes smaller, that's our zooming factor, and we look at it closely. But no matter how close we look, we will still see this 90-degree angle. It doesn't start to level out. So it's not differentiable at that point because it's not flat when we zoom in on the origin, right? In other words, again, returning to this definition here, we can define the error there. If we follow some straight line, the error itself would go to zero, but once we multiply this, this h times the error goes towards zero. But if we look at the error itself, this deviation is in fact actually equal to this absolute value of h. That's the scaling factor. The deviation will be always equal to the scaling factor if we zoom in on the origin. So this r of x in this case would be 1. Its limit is not going to be 0 as we zoom in more closely here. So this is my h now. This is my error here. So this doesn't go towards 0. So when we zoom, for this to be differentiable, this slope should become, what do you say? What's the opposite of steeper? You know, it becomes less and less steep until it's completely horizontal here. Because this and this as well. So we should approach a situation where it's completely horizontal here, which it is not. Okay. There are other cases in which the derivative doesn't exist. So the thing that happens in this is we take the cubic root of x and we zoom in on the origin. Then here, this goes a bit contrary to what I said. Yes, it looks like this line becomes flatter, but in fact it starts becoming vertical. And you know, there is no linear function that draws a vertical line. So that's why it doesn't exist. In fact, what happens is we can say that the derivative itself here, the derivative itself, if we think about the secant line or the second line, in this case, depending on are we moving left or right, that always has slope 1 or -1, but it doesn't converge to some slope that is the same when we approach from the left and from the right. Here, we do get a kind of similar behavior from both sides. The problem is it tends to go to infinity. So this, if we find this limit here, it becomes an indefinite limit. It goes towards infinity as x goes to 0. So this is differentiable in all other points except at x equals 0, and it's continuous, but there's no angle there. It's just that it's vertical at that point. So this is a sort of pathology that may not be, you may not think that it's such a big deal. It's not such a big deal in drawing a picture like this or considering this is continuous and what have you. The problem with this is, of course, that then, you know, when the derivative goes to infinity, then there are all sorts of nasty things that happen if we have these kind of functions and we try to solve certain differential equations or something like this. So this at zero, these become problematic. There are other functions. There's like this x times the sinus of 1 over x. It wiggles very, very vigorously as we approach zero. X makes the function itself go towards zero, because that's, if you look at the limit of this, if you look at the limit of this f of x here, x times the sinus of 1 over x. So we know that this sinus of 1 over x, it may be somewhere between -1 and 1. But if x is very small, then the epsilon delta characterization gives us that this function will have a limit, both-sided limit. Both sides approach zero, you know. So the limit, this is continuous, and it has a limit at zero, at zero, as f of 0 is equal to 0, and the limit of f of x when x approaches 0 is also 0. So this function here, as defined like this, is in fact continuous at 0. The problem with the derivative here is that we can't really say anything about the derivative, because the derivative, it goes up and down, and when we start zooming it, if we start zooming in on the origin in this picture, then it's just going to be looking like this. The picture will look like this all the time, right? It will look, all the time it will look like this. No matter how closely we zoom in on this, it will just look like this. Like, you know, like we're in a, it would be nice to have an animation of this. If we zoom in on this, then the animation would look like, you know, there are wiggling sinus waves coming out of the origin like this at your face, and you're just traveling into the origin, zooming in, and just seeing the similar picture repeat itself all over again. So this is an example of what we call the fractal behavior of a function. So it doesn't have a derivative at 0. The reason is that you know, the derivative gets more and more different values when we get closer and closer to 0. Because that's, you know, it's like the limit as x goes to 0, 1 over sine of x. And it's weird. It's weird. Okay. Here's a summarization of the connection between continuity and differentiability. Non-continuous, if a function is not continuous, it cannot be differentiable. But if it is continuous, it doesn't have to be differentiable. So if it's differentiable, it's continuous. But if it's continuous, it may not be differentiable. Here's a thought about piecewise functions, continuity and differentiability. And I'll put an example. There was an example of a function determine a c such that that function is continuous. And now for next week's exercises, I will have determine b and c such that that's differentiable. Here's an example of a situation like this. You can look at it. I'm not going to spend the time here because it takes a little bit of time, but you should be aware of this, that, you know, there's a one function in a one piece, another function in one piece, and you need to find these constants in such a way that this f of x itself, you know, this gets the same value as this at -10. Not only that, but the derivative of this must be the same as the derivative of that, so that it has a derivative at you can find it differentiable at -10, because the limit doesn't, otherwise it doesn't exist, right? So here's an example. Please go through it, and I'll put one weekly exercise task for next week, which covers a similar matter. Here are two examples, or you know, of that. I'm not going to talk about higher order derivatives. Why? Well, I am going to say something, but not going to focus too much on that. We don't want to calculate them directly, because, you know, you find the derivative function, then that's just a function. Find it again, that's the second derivative. I mean, derivative of the derivative is the second. We can have the, and now understand that the derivative can be thought of as an operation, just like taking the negative or taking the inverse or taking the whatever. The derivative is a operation that you can impose on a function and out comes another function. That's important, right? It's an operation on a function. Then we get, so putting the prime, if we have f of x, take the f prime of x. So you can think of it that way. Usually we use this dy slash dx over dx or d over dx. That putting that d over dx in front of a function means, okay, take the derivative of that function and then that's your result of this operation. So the operation is differentiation. And high order means just apply differentiation once, twice, 3 times, so forth. So this happens. Why do we need higher order derivatives? Well, there was also mentioned an example that the speed of an object, the velocity of an object can be thought of as the derivative of the place, the rate of change of its place. So its acceleration can be thought of the rate of change of the speed. So if we're thinking about one-dimensional case, so it's going at, let's say, assume that the trolley is moving on the x-axis, and the time gives us where it's at a given time. So d over dt of that place is the speed, and d over dt of the speed or the velocity is the acceleration. How fast is the speed moving? If the acceleration is negative, then it's braking, and if it's positive, then it's accelerating, right? And these kind of things, the second order derivatives, they occur a third order, fourth order, just higher order derivatives. They appear in differential equations and modeling of things. Like if you model a car, so who is familiar with cruise control in cars? I hope some of you are. So you can just, you can set the computer so that to maintain the speed at this current speed. Okay, seems easy enough. The thing is, what does the computer need to do? It needs to find, it cannot directly affect the speed, right? What it can do is it can either accelerate the engine or, accelerate it more or less. So what it does is, and I'm not going to go into details, but when the speed is over that, it'll loosen the accelerator, give less gas to the engine. And if it's going slower, it'll give more of it. That's it. But that doesn't, that accelerate, that gas pedal, you're giving it, the accelerator pedal, if you're pressing it more, then if you press it, that's not the derivative of this place. That doesn't give you speed directly. What it gives more fuel to the engine, which then makes the engine run faster, which makes the car accelerate. So that's actually the rate of fuel that goes into the engine is the accelerator. And the rate of fuel that goes into the engine is not even directly the rate of acceleration. It's probably some rate of acceleration increasing up to a certain point and so forth. So it's very complicated. But this can be modeled with differential equations, and they will necessarily involve first, second, even third derivatives. Not going to go into details, but you'll see examples of that later. Here were examples, finding acceleration and so forth. All right, so now to the important part, differentiation rules. And one of the things is, in mathematics often is, this is an example of what we call compositionality. It means that if we have some operation that we're going to be doing, and in this case, the derivative or the differentiation operation. And not going to go into these rules quite just yet. Not going to go into these rules quite just yet. We just explain very quickly what we want to do. We want to show that the operator, here is the operator, that is finding the derivative operator, the d over dx, the f prime of x, right? The prime operator, if you will. Then a couple of things that I want to say about it. And the first thing that is important is that it is a linear operator. It means that the derivative of a times f of x is a times the derivative of x, f of x, sorry. And the derivative of the sum is the sum of the derivatives. And that's linearity for you. Look at this. This is a real function here. Sorry. Where was it? This is a real function, but let's say that we are dealing with some abstract space. And let's say we're talking about functions. So the operator, as an operator, the differential operator or the derivative as an operator is simply something that takes a function and transforms it into another function. And that function can be multiplied by a constant. If it's multiplied by a constant or if two functions are added, then the result can be gotten by multiplying by constants and adding the derivatives. So the derivative itself is linear. Concept of linearity is very, 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 very powerful in mathematics, and it's like a template for thinking. So it's not something that is limited to real numbers and so forth. It's linearity is everywhere. So let's first look at this. So we can build these from a couple of rules. So let's start from the basic rules that the derivative of the constant function. So we have, remember that list of elementary functions. So what we know now, and we'll just return to that list. So I'll just go up. And I'll just, functions, elementary functions. So we have constant functions, power functions, exponential functions, logarithmic functions, trigonometric functions. And all functions obtained by adding, subtracting, multiplying, dividing, and composing the previously listed functions. Okay? So the way we can find the derivative for all elementary functions is by looking at the simplest cases of constant functions, power functions, exponential functions, logarithmic functions, trigonometric functions. Not even all of those. It's actually enough for us to look at constant functions, power functions, and exponential functions. And then maybe at some point, I mean, maybe for your purposes, the trigonometric functions, but not the logarithmic we can get, because it's simply taking the inverse. And what happens to the derivative of the inverse? It's not really the inverse of the derivative. I'll show you that, but something happens when you add, subtract, multiply, divide, or compose functions, and then take the derivative of that. And if we can derive what happens to the derivative operator, what does it do to the composite function, then we can, no matter what function is given to us, we can just piece by piece, purely mechanically solve the problem. No ingenuity, no creativity, no anything like that is needed. Okay. So let's start with the constant function. Well, the constant function is notoriously easy because if we find the difference quotient here, f at x plus h and f at x is c when we are dealing with the constant function c. So it's always 0, and it doesn't really matter what value h gets, that's going to be 0. No matter how close to 0 h gets, 0 over h is still 0. It's not defined as h equals 0, but the limit is definitely 0 because it's 0, on both sides. So the derivative of a constant function is always 0. Well, that's an easy peasy. You knew that already, but from this definition, it's fairly easy to. And it's the same thing. I mean, if you think about the constant function, it's a straight line. Its slope is always 0. The graphical interpretation. The power rule, that's powerful. So here are some examples, but let's go first to the rule at which we can prove directly. And this proof is something that this is the first theorem that I really would like you guys to study and understand how it works, because this kind of a reasoning is very common in deriving novel mathematical rules, mathematical theories on just proving something. And you know, you may not aspire to become mathematicians here if you're just studying this as a part of your curriculum to study some engineering. But there are cases where this gives you a kind of like a intuition or understanding why this happens. Why is it so? So understanding why something is so, it often comes from the proof. So I'm of the opinion that simply memorizing a formula is not really, it's not very productive for understanding the topic. So let's see what happens to the power function, x to the power of n. And for illustrative purposes, we let n be equal to some positive integer. This in fact works for real numbers as well, but it's somewhat trickier and somewhat harder to prove. So we just prove it for positive integers. Once we've proven this for all positive integers, we can actually build stuff. And then for addition and multiplying with a constant, then we're really done. We're really done with most of the stuff that deals with polynomials. And we can calculate the derivative of all polynomials after these. So let's start. If f of x is x to the power of n, then its derivative is n times x to the power of n minus 1. You can memorize this, you probably have memorized this, but why is it so? And this is really the fun stuff here. So let's look at this f prime. So it's the limit at x plus h to the power of n minus x to the n divided by h. And what happens here is that you can forget about the rest of the formula, but using the binomial formula on this x plus h to the power of n, then we have first x to the n plus, and then we have n times x to the n minus 1 times h. And then we have some terms where there's n to the minus 2, sorry, x to the n minus 2, h to the 2, then so forth. And the last term here is h to the n. So that's the binomial formula. That's simply outright written. And if we then use this to eliminate the h, then we notice that firstly, this subtraction here, it's going to subtract this xn, so that's going to disappear. If we divide by h, this h disappears from here, right? So what is left is n times x to the n minus 1. But then here, the h to the 2 becomes h to the 1. So that's just h, that h to the 2. So all these terms at the latter part of the formula, they all contain h to the power of at least 1. And then we've canceled out this h completely from the limit. That's what happens here. In this case, this is what happens. So there's that is the only element that has no h in it. All the others have at least h to the 1 or more. And as h goes to 0, all this highlighted part goes to 0, obviously. The only part that is left is n times x to the n minus 1. So as that is the only thing that is left, that's the derivative. You already know, should know from high school mathematics or whatever, you should know the way to apply this power rule. I'll put some exercises next week where you apply the power rule. That's fine. So another theorem, and this is really important. This comes down to proving the linearity of the differential operator. So the important part is that if we have two differentiable functions, f and g, and we find the derivative of f plus g, then it is in fact the derivative of f plus the derivative of g. And here's a proof, and we only need it for the sum rule. So let's very quickly go through the proof, how it goes. So we mark with J f plus G. So J at x plus H, and that becomes at f x plus H plus G at x plus H. So this becomes the limit of two sums. But because the limit of sums is the sum of limits, then it just comes down to those two limits, which then are by definition the derivatives of f and g. So the minus, the blah, 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 that's not, we can forget about all that nonsense about minus being somehow different. This is sum. So we take sum, that works. And then the constant multiple. Well, the limit, because the limit has the multiple. Remember, we proved that if the limit of something is L, if the limit of f at some point is L, then the limit of k times f at that point is k times L. So we know that for arbitrary A and B, and let's look at this again. For arbitrary A and B, these are now the constants, and let's say this x and y, forget that this says R, think that f, these are functions, then the derivative of A times f, or A times x, where x is a function, plus B times y, where y is another function, is A times the derivative of x function plus B times the derivative of y function. So think about that in that terms. So these two rules really give the linearity of the differential operator. So this gives us a very powerful tool. These two rules together, the constant multiple and the sum rule, they together give us an extremely powerful tool for handling everything. So in fact, we've now proven everything about how we can now find the derivative of all polynomials. We've already covered that now. We know how to do that. Here's some derivative rule examples. Not going to go there. We'll find those during the exercises. We'll go through these a little bit. And an important rule here is also the product rule. So this is a bit harder. So if we multiply f and g and find the derivative of that, then it's not going to be the derivative of f times the derivative of g, because it's going to behave a little bit differently. So why? Well, let's take a look at this proof. I think it's easier to do it following this. So let's again mark j of x as fx times g of x. So we find the derivative of that. So we find this multiplication becomes here. So that's our j at x plus h minus j at h. So how do we find this in terms of f and g? Well, we do this, we both add f times f at x. So this term here, it's both added and subtracted here. So we take fx times g of x plus h. We both add and multiply it, and then rearrange. And when we rearrange this, here we get limit as h goes to 0. We have here f of x plus h times g of x plus h minus f of x times g of x plus h. So this g of x plus h can be taken as here as a multiplier, and in here also we have f of x here as a multiplier for this g of x plus h minus g of x. So this again, this clearly about, because remember here g is continuous, so this approaches g of x, and this limit here, the limit here is definitely the derivative of x, And this one here is already f of x, and this is the derivative of g. So we get that the derivative of f times g is the derivative of f of x times g plus the derivative of g of x times f. So again, this is a very highly important rule that you really must remember. I mean, I hate to say this about these rules and formulas, but this is something that must be remembered. You cannot, if you misremember this, you will get most of the differentiation problems wrong. That's going to happen. That's the product rule. Here were binomials, but this really makes very little sense applying it to polynomials, because polynomials you can just write them out and find the derivative in parts. You know, just not going to go into the quotient rule. You could, but not going to go there now. The divide f of x over g of x. It's very similar to the product rule. I think it's far easier for us to just omit it now. The theorem here extends the rule to power to negative integers. In fact, it can be proven to work for all real numbers, non-zero real numbers. Not going to go there. Now we can use these rules and subsequently, you know, just use them one by one. We can apply the product rule, here if we have 3 times h of x, and find the plus x squared times g of x. So we can use the first of all, this is a sum, so the derivative of the sum is the sum of the derivatives. We can use the constant multiple rule here. So this is 3 times the derivative of h. And then this is a product, we use it there. So we use the product rule, it becomes the derivative of x squared times g plus the derivative of g times x squared. And we come up with this nice formula here that's the derivative of the original function. No need to extend the product rule to three functions, because, you know, obviously you can apply it twice. Once for one function pair that is multiplied, so once for f times g and h, and then you get some f times g derivative and g times f, you know, h derivative times f times g, and then you apply it again to the one where you have to find the derivative of f times g. So it's given here, so there's no need for us to go through this, because you know, why would you extend the product rule to 3? Because there's just 2 products and you use it twice. That's all there is to it. The horizontal tangent is very important situation. It's this, what does it mean that the tangent is horizontal? If we find the horizontal tangent, that is simply the situation where the slope of the derivative is 0. So finding the derivative 0 is an important problem. We all know by now, I mean, I hope you know from previous courses that that's an important question. Yes, true, fine, but it's simply find the derivative, set it to 0, and solve the equation. Nothing more to it. But obviously it has a special case. It means that if the slope is 0, then it means that there is one of 3 things is happening. It's going to go up on the left and up on the right, which means that in this case it's the minimum. It's going to go up on the left and down on the left and down on the right. So it's going to be a maximum locally, or it's going to be up from the left and up from the right, in which case it's just what we call a saddle point. All of these 3 will happen. The real interesting question is that if it goes up from both the left side and the right side, and the slope is 0, then we know that it's a minimum. We'll talk about this a little bit more later. Not going to go there with this. And we'll talk about the finding the minimums and maximums later a little bit more. All right. So let's look at some of the exercises. Let's do this in groups. You may want to do something. Let me see, where was it? I was thinking about this. Okay. Here it says find the equation of the tangent line to this graph of this. See, so really find the derivative. So these are all derivatives finding problems. So using these rules, what I want you guys to do is, instead of doing it in a way you learned at school so that you just do it one by one, every time you do one step of the way, then start from the whole formula and then break it down. Explain, here I'm going to use this product, the derivative of the sum, and it's the sum of the derivatives. And then when you do it for one, I'm going to use the power rule. I'm going to use the quotient rule. I'm going to use whatever. Just do it in a step-by-step manner so that you carefully explain which rule or what kind of reasoning you use on each step of the way. And we'll get to this more nuanced or more accurate or more detailed derivatives shortly. So do that for this very simple. Let's see, where was it? I was thinking of this. Something that doesn't, what was it? I was looking at this example a while ago. Okay, 148. Find the derivative of x to the, of f of x is equal to x to the 3 plus 2x plus 3 divided by x, assuming x not equal to 0. All right, and I'll put you into those rooms. You have about 10 minutes, or let's say you have 8 minutes to do that, and we'll just look at that then. All right. Now, so I'm not really that interested in what the result is. I'm interested in a sequence of ways on how you go about this. I hope you got some discussion going on about that, how it's done. So the way I would suggest that you do this is first you simplify it, because there's that x, then simplify it to x squared, simplify it to x squared plus 2 plus 3 over x, which is then 3 times x to the minus 1, right? This is not yet finding anything about the derivative, but you simplify it to this, and then you use the sum rule. Find the derivative of x squared, which is 2x, by the so this is plus, and 2 becomes, that's 0 plus 3 times x to the minus 1. Applying the rule there, we get minus 3 times x to the power of minus 2. Right. So, you know, one by one, you do this each one. So first apply it to the sum, all of the sum terms separately. To the x squared, that becomes 2 times x by the, you know, the using the rules were power rule constant. So I write it like this: power rule plus constant plus power rule. Right. That's what I was looking for. And there is no need for the next week's exercises to do this for all the formulas. It's not necessary, but I do wish that when you do this for some of the formulas there, then if you are in doubt, mark them down, and at least think about it in these terms. Try to be aware of what it is that you are doing. Right. I didn't get to the part where I would have loved to have some more rules about there. I'm going to skip this part. The trigonometric functions we still didn't cover. Those we need to cover. The exponential functions, sadly, we have to talk about them a little bit more on next week. And the chain rule. The chain rule is highly important. It's really important, so that because we will be able to, sorry, we must be able to talk about the composition function. So state the chain rule for composition of two functions. I hope that you will read this. We'll try to go through this rather quickly next week, because we need to cover a little bit more ground. I think I'm going to have to change the agenda a little bit, because I was too optimistic about the speed at which we go through this material. So we'll continue with the chain rule and the trigonometric function rules on next Tuesday. All right. I think we're starting to run out of the time that I promised this would take. So I'll update, what I promised to do on next Monday is I'll update the agenda for next week and following weeks as well, because it seems we're lagging behind. I had luckily reserved one extra week, so we'll be able to cover the whole ground of this. Are there any questions now?
I have questions about practicalities. So I tried to assess like a previous homework, but I cannot save anything, and I didn't find place where to put grades.
Okay.
So,
anyone else have the same problem?
Yes, I also wanted to ask that. Like, it allowed me to save and continue, but when I do that, it like doesn't integrate my assessment into that, so it still say not assessed.
Okay. I'll try and fix that. Just a second.